Hi, this is Mrs. Frobel. This is Chapter 13, Gases, Part 3. In this video, we're going to be talking about using the ideal gas law. And with the ideal gas law, we relate the amount of gas. It's now no longer a constant, and we're related to pressure, temperature, and volume. In this video, also, we're going to talk about the properties of real versus ideal gases. And then lastly, we're going to correctly determine molar mass and density of a gas with the ideal gas law. Now this is section 2 of your book. So we're going to take actually all three laws, Boyle's law, Charles' law, and Avogadro's law. And if we relate it to volume, now that symbol in the middle there, that's called a proportion. We can actually combine these three together, and what happens is we get this equation here. And we can take out that proportion sign and make it an equal sign. Now, in order to do that, we actually have to get a constant, and we call that an ideal gas law constant. Notice it has the letter R, so anytime you see the letter R, we're talking about ideal gas constant. Okay, so the different versions of R, and you need to pay attention to these. This is where a lot of students run into trouble. It's the pressure unit that really tells you which R value to use. So if you have atmospheres, you use this one. If it's kilopascals, you use that one. If it's millimeters mercury, you use that one. So you have to pay attention to the pressure. Okay, with real versus ideal gases, notice that ideal gases, they don't have attractive forces. They have elastic collisions. They also take up no space. However, real gases do have attractive forces. Their collisions are no longer elastic, and they actually occupy space. So when does this happen? Well, usually it happens at high pressure. The molecules are forced together, and as a result, they get sticky and they start to condense into a liquid. Or maybe if you have low temperature, they're removing the kinetic energy, and as a result, the attractive forces take over. Okay, so what I want to do is go over a problem with you. So using the ideal gas law, we're going to use the following equation: PV equals nRT. And because it says STP, our atmosphere is going to be 1 atm. We don't know the volume, so I'm putting V. The number of moles is 0.0459. And because of the pressure, our constant is 0.0821, and that's liters times atmospheres times mole Kelvin. And then our temperature is 273 because it's standard temperature and pressure. So when you solve for V, you get 1.03 liters. Okay, I want you to practice using this problem, and we'll do it in class. Notice that you're looking at grams, okay? So you should be solving for moles, and then once you get that, you should be able to convert it to grams. Okay, so density. Density is D times V equals molar mass. So if you wanted to change the volume of a gas, but you kept the mass the same, you would find that the density is actually inversely related to volume. So if you increase the volume, density should decrease. By the way, M is molar mass. Okay, so what does this mean? With gases, density and pressure are directly related. You increase density, you increase pressure. Whereas density and temperature are inversely related. You increase density, temperature decreases. Now, just as an aside, this is density equals molar mass divided by molar volume. And when we're looking at molar volume for STP, remember it's 22.4 liters. If it happens to be standard state, it'll be 24.5. And you should know that first constant. The second constant, I'll give that to you. Okay, here's another problem. Here, if we relate pressure, volume, and temperature together to density, so we replace V1 with molar mass divided by density, and V2 equals molar mass divided by the second density, we can get this equation. So we can actually use it with the following problem here. Notice that O2 has a certain density, and they want to know what is its new density. So how do you set that up? So you put pressure on top, so 1.0 atm divided by the density, which is 1.43 grams per milliliter, times temperature. At STP, it's 273 Kelvin, equals the second pressure, which is 0.5 atm. I don't know the new density, so I'm putting that down here, and I'm going to multiply it by the new temperature, which is 373 Kelvin. And then I'm going to solve for D2. So I'm going to put the variables off to one side. Okay, so D2 is 0.5 atmospheres times density, which is 1.43, times the temperature at STP, which is 273 K, and that's all divided by the second temperature, which is 373 K. And when you solve for that, you should get 0.523 grams per milliliter. Okay, so the summary is ideal gas laws relate the amount of gas, pressure, and temperature along with volume, and the equation that you use is PV equals nRT. At very high pressure and very low temperature, real gases behave differently than ideal gases. And then lastly, the ideal gas law can be used to find the molar mass of a gas. So the molar mass is equal to mass times R constant times temperature divided by pressure and volume, or density equals molar mass times pressure over R constant times temperature.